All right. Hello, everyone. Today is March 30th, Tuesday. It's a Tuesday late evening. It's the fifth week of the spring semester. Hope you guys had a great weekend. Stay healthy and doing well and enjoying the spring semester. Uh, I apologize for a delay. First of all, I was supposed to take this video yesterday, but I don't know why. But every Monday, there are so many things to do, and there are so many things distracting me. So I had no enough time for recording this lecture video. And furthermore, I had a sore throat yesterday because of a heavy fine dust and even yellow dust. And I think you guys saw that whole country was plagued by every kind of dust. So it was not a pleasant day. Uh, still I'm suffer from a sore throat, so cannot speak loudly, but I will keep up the steam to finish recording lecture videos until tonight. So hopefully I can upload lecture videos until Wednesday morning. So this week my aim is to cover the entire chapter 6 and part of chapter 7, and there are 4 topics, and I'm planning to record one video for each, so there will be total 4 videos uploaded on my YouTube this week. So it sounds like many topics, but I guess you guys have seen this you guys are very familiar with most of these topics, so you can easily follow up. So we finally move on to part 3 in the textbook, the new topic, comparative static analysis. So we are kind of done with linear algebra. So in past 2 weeks, we studied how to solve a system of linear equations using matrix algebra. Uh, and of course, linear algebra is a large branch in mathematics, so it's almost impossible to address every single topic about linear algebra in just the 2 weeks. But I think we did cover the most important ones. So I guess you guys have no trouble with understanding linear algebra, especially when you take some advanced economic theory class or econometrics class. And furthermore, I will supplement our course material by tackling on some challenging problems together at the live lecture this Friday. So I guess those materials will help you understand linear algebra further, especially the operation of matrices. So I think that will be enough for us. So now let me move on to a new topic, comparative static analysis. And I introduce its basic idea in the introductory video, just to remind you of this analysis. Comparative static in economics is the comparison of two different equilibrium states before and after a change in some underlying exogenous variables. So we can think of several changes in variables or changes in several variables. For example, tax reduction or subsidy provided by the government, or we can think of an increase in price of other products, or we can think of a network effect. In all of these cases, demand curve will shift up or shift to the right, as is displayed in this diagram. So demand curve will shift from D1 to D2 if there is a tax reduction or subsidy for electric cars, for example. Or demand can increase in case of increase in price of other substitutes. For example, if you think about the relationship between iPhones and Android phones, if the price of iPhones goes up, then some customers may want to switch to Android phones, so thereby increasing demand for Samsung Galaxy, for example. In the presence of network effect, demand also increases. So if you see all of your friends using the same particular product, you may want to use that product as well. So in all of these cases, demand curve goes up, and as a result, there will be an adjustment of endogenous variables. So we are going to study this adjustment process at the end of this course when we study optimization theory. So putting aside this adjustment process for a second, if we just focus on transition of equilibrium, uh, then we have two intersections in this diagram. The first intersection is a intersection between D1 and S. So this is a old equilibrium, and this is a new equilibrium. And by comparing these two states, we can easily see there will be increase in price and increase in quantity. So this is a very simple example of comparative static analysis. I guess you've ever seen this kind of a diagram many times when you took the principle of microeconomics, for example. And let me illustrate one more example to, for motivation and to illustrate why we need to pursue this kind of an analysis when we study economics. That is a example in the previous week lecture slide. So going back to lecture slide previous week, and there is a one example I couldn't entirely cover at the previous live lecture. That is a market model. So in this model, there are two commodities, and using matrices, we express the equilibrium conditions this way, and we solved for P1 using Cramer's rule to obtain this expression. So we express the equilibrium price of a good one as a function of several parameters. And using this formula, we can do some comparative static analysis. For example, we can investigate the equilibrium effect of a tax. So for specific example, suppose that a central authority attempts to impose a sales tax on each commodity one produced. So this tax T is not imposed on consumers, but imposed on producers. Okay? And one specific example is commodity one is a plastic. So government wants to protect environments by imposing this tax T on plastic. All right. And if that tax T is imposed on producers, then there will be some change in supply curve in market one of commodity one. And previously, before tax, supply curve is given by B0 plus B1 times P1. And here B1 stands for price elasticity of supply. So as B1 gets larger and larger, quantity supplied will be more sensitive to change in price, right? So in this sense, B1 stands for price elasticity of supply. So if tax is imposed on producers, whenever they produce 1 unit of plastic, then such a tax T will decrease this B1 because such a tax T creates a wedge between market price consumer pays, that is still P1, and the actual price the firm receives from selling 1 unit of plastic, that is no longer P1, but 1 minus T times P1, because the firm has to pay tax as much as T times P1. So imposing tax T producers is equivalent to reducing the size of B1 from B1 to B1 times 1 minus T. So B1 will shrink to this value. Okay, so with that in mind, if we look at the impact of such a tax on equilibrium price of a good one, then we just simply look for B1 terms here, and there is a no B1 in this bracket, and I can see B1 terms on the denominator. So because the tax T decreases B1, so if B1 decreases, we divide the same quantity by a smaller number, so as a result, P1 would increase. Okay, so that is a one result from we can obtain from comparative static analysis. But we can draw this conclusion, the same conclusion, even from partial equilibrium analysis. So think about so if we draw the diagram, so this is a x-axis, for Q1 and y-axis for P1, and we can draw the demand curve and supply curve in market 1. So if tax T is imposed on producers, and you can easily expect supply curve will shift to the left like this, because at each price, such a tax T undermines the incentive to produce and supply units to the market. So the quantity supplied at each price will decrease. As a result, demand supply curve will shift to the left like this. So we have a two equilibria here. So we can see equilibrium will change from this point to this point. So the market price will increase. So the price of a good one increases, but the quantity demanded and supplied will decrease in this market. Okay. So we can draw the same conclusion even from partial equilibrium analysis. Then why we have to look at the other market? Why we have to consider interdependence between market 1 and 2? Because by considering interdependence, we can say a little bit more from this comparative static exercise. So now think about the market 2. So if we focus on C2 and D1, and C2 is the price elasticity of demand in market 2, and D1, elasticity of supply in market 2. And if C2 and D1 get larger and larger, then the expression in this bracket will increase. The quantity of this expression will increase. So the increment of P1 would increase. On the other hand, if the second market is less sensitive to change in price, so economic forces, demand and supply are less sensitive to price change in market 2, so C2 and D1 takes a small number, then the increment in price will be smaller. Okay, so what does it mean? Because if we have a market 2 and the increase in price 1 is not the end of the story, because customers in market 1 will respond to increase in price. So they no longer consume good 1 and rather switch to commodity 2. So stop consuming good 1 and start consuming good 2. Right? So now we consider market 2. So here Q2 and P2 and demand curve and supply curve. Right? So if some customers switch to market to commodity 2, there will be increase in demand like this. Okay, so if the price of a good 1 is expected to increase and some customers will switch to commodity 2, then there will be increase in demand. So the price of good 2 also increases. All right, and suppose that the customers are really sensitive to price increase in with respect to commodity 2. And if they expect price increase in market 2, then the number of customers switching to market 2 will be very small. So because a price is expected to increase in market 1, so some customers will switch to market 2, but the number of such people will be very small. So the demand curve will shift down, but just by a small amount. Okay, so the new equilibrium price will be formed at this point. So the comparing with the previous equilibrium, still we can expect a large increase in price of good 1. Right? That is the case when the price elasticity of demand and supply is really high in market 2. But suppose that customers are less sensitive to price change in market 2, then we can expect a lot of people switching to market 2. So there will be a large reduction in demand in market 1. So now the demand curve will decrease will shift down to, this dotted line. Okay, so the new equilibrium will be determined at this intersection. So comparing with the previous equilibrium, there is a no change in price, right? So the increment in price of a good one as a result of tax T depends on price elasticity of demand and supply in market 2. That is a additional insight we can gain from doing comparative static analysis. So if you wonder why we do comparative statics in economics, we can find exact causality between two variables. Just as in this example, we can see the relationship between some sales tax and the equilibrium price and the price elasticity. And then we can specify a relationship between those variables by doing comparative statics. Also, we can enrich our economic insights by doing such analysis. Right? So we can learn some additional effect on equilibrium price that is a price elasticity in other market. So that this is why we pursue this kind of analysis in economics. Right? Hope it is clear. And now let me go back to our lecture slide. And this analysis can be divided into two, qualitative analysis and quantitative analysis. And qualitative one pertains to direction of change. Uh, so if you live in South Korea, you guys know that under current regime, the government implemented and amended housing law 25 times in the last 4 years to decrease the real estate market price. So we can ask, does the newly implemented housing law cool down the real estate market? That is related to whether property price increases or decreases. So direction of a change. Or we can think of a quantitative question. That is if the government provides a child care subsidy, then we can expect an increase in the fertility rate. But how much increase can we expect from such a baby bonus? Okay, that is a qualitative question. So depending on the economic questions, we can carry out qualitative analysis and quantitative analysis. But when it comes to comparative static analysis, the main problem under consideration is essentially one of finding rate of change. So for qualitative questions, the question boils down to whether the rate of change takes a positive value or negative value. So if two variables move in the same direction, so as in the previous example, if the government imposes a higher property tax rate for property owners, whether housing price goes up or down. So if these two variables move in the same direction, then the rate of change will take the positive value. If they move in the opposite direction, it takes a negative value. So the qualitative question bears on the sign of the rate of change. And by the way, this letter, triangle, that is a Greek letter called delta. And it is commonly used to denote changes, the amount of change. Okay, so this delta of a housing price means change in housing price. Okay, and for quantitative questions, now we consider the magnitude of the rate of change, the size of rate of change. So in the previous example, if the government provides a baby bonus, how much increase in fertility rate, that is related to size of this rate of change. So now we are investigating the value of this rate of change. Okay, that is a quantitative question. All right, and regardless, there is a nice tool in mathematics when we investigate the sign of the rate of change or the magnitude of the rate of change. That is the so-called derivative, which is the most fundamental concept in the branch of mathematics known as differential calculus or just the calculus. And that is a really nice tool, a very effective and practical tool whenever we carry out comparative static analysis. So from this week, and I think it takes a 2 or 3 weeks, we are going to, so we pay attention to finding derivatives, and we are going to study several properties of derivatives. Okay, so in this video, I'm just I just introduced the definition of the derivative. All right. So the derivative is just a one rate of change, more specifically, instantaneous rate of change, and we are going to define sooner or later, I think in 5 minutes, right? And let me first define the rate of change, right? And for this purpose, we have a one function between two variables x and y. So y equals f of x. And remember, the argument x, the argument of a function, is called a independent variable. And this y is called a dependent variable in the sense that the value of y depends on value of x. Okay. And if we change the independent variable x from initial value x naught to new value x sub 1, so we increase x by h, okay, then the function will change from f of x naught to f of x1, okay? And the rate of change is defined as the ratio of these two changes. So we usually put the change in dependent variable on the top. So delta y, that is a change in variable y. So that is a difference between f of x1 and f of x0. And the change in x on the bottom. Okay, so difference between x1 and x0. So in terms of h, the increment of x, we can rewrite this as f of x naught plus h and minus f of x naught and divided by h. Okay, because x1 is simply x naught plus h. Right? So here h stands for change in x, and the change in y can be expressed as the difference between these two. All right, and I think you've ever seen this. So you've seen this expression several times: change in y and change in x, and that is nothing but the slope of a linear function. So whenever y is given by ax plus b, meaning that y is increasing at the fixed ratio a whenever x increases or decreases. So for linear function, the rate of change is fixed by the slope of the linear function a, regardless of change in x. But for nonlinear functions, the rate of change indicates the average change in value y in response to a unit change in x over some specific interval. So if x changes from x0 to x1, and the corresponding rate of change indicates how much value y changes on average in response to unit change in x. All right, so to help you understand this interpretation, let me show you one example. So here we are given one nonlinear function, y equals 3x squared minus 4. And if we find the rate of change due to change in x from 1 to 4, then we can first compute the change in y. So when x equals 1, y takes 3 minus 4, that is negative 1. When x equals 4, y is 3 times 16, minus 4, which is 44. So the rate of change delta y over delta x, y changes from negative 1 to 44. So 44 minus negative 1, and x changes just 3. So 45 divided by 3, that is 15. And the meaning of this interpretation of this number 15 is when x changes from 1 to 4, so over this interval between 1 and 4, y changes by 15 units on average. Okay, so if x changes by 1 unit, then the y correspondingly changes by 15 units on average. Okay, that is a interpretation of rate of change. So if there is some discrete change in variable x. Okay, and geometrically, that rate of change, the rate of change measures the slope of the sequent line. So here we have a one cost function. So cost C is a function of quantity produced. So if we think about a rate of change of this function over this interval between Q0 and Q2, okay, then the rate of change is going to be sequent line. So the 2 points A and B, the line connects 2 points A and B on the graph, and the rate of change is going to be the slope of this sequent line. Okay, so it tells us if the firm increases a quantity supplied from Q0 to Q2, the average increment of cost per each unit. So that is a average cost, right? So the rate of change over some interval is that means the average cost to the producer, to the firm. Okay, so the rate of change is derived from the slope of the straight line A and B over this interval. All right? And there is a counterpart, instantaneous rate of change. Okay, and for motivation, because most economic variables, for example, oil prices and interest or exchange rates and stock prices can change infinitesimally in a short time. So for analysis of such a variable, we sometimes look at instantaneous rate of change. All right. Furthermore, in economics, there is a long-run analysis and a short-run analysis. So sometimes we want to look at how some variables respond in a short space of time. In such a case, we look at a instantaneous rate of change. That is defined as the rate at particular instant. So mathematically, it's defined as the limit. Now we have this notion limit. So the limit of the rate of change as the change in x goes to 0. Okay, so it gives us how does a rate of change respond as a delta x. So change in x is very close to 0. Okay, so in other words, because delta y, change in y, is going to be the difference between these two quantities when x changes by h, right? So now we take the limit as this increment of x go to 0. Okay, so that is a instantaneous rate of change at some particular instant or particular point x naught. Okay, so we are going to study this expression over and over from this week because this is a definition of the derivative. Okay, so just for exercise, given this nonlinear function, quadratic function, if we find out the instantaneous rate of change at x equal to 1, then we can simply put in 1 for x naught, because we are looking for instantaneous rate of change at this particular point. And now we can compute each component in this definition, in this expression. So f of 1 plus h. So if we take this function, f of x, then f of 1 plus h is a 3, 1 plus h squared minus 4. So which is, so if I expand 1 plus h squared, then I would get 3 plus 6h plus 3h squared. So take away 4, then I will get 6h plus 3h squared minus 1. And f of 1 is 3 minus 4, so negative 1. So the difference between these two is going to be, because we can cancel off these two negative 1, so f of 1 plus h minus f of 1 is 6h plus 3h squared. Okay, so that is the numerator of the instantaneous rate of change, and we divide it by h, so then we'll get 6 plus 3h, and 6h becomes 6, and 3h squared becomes 3h. Now we take the limit as h goes to 0. So if h is very close to 0, this 3h goes away. That's 3h also very close to 0. So the limit value of this guy as h goes to 0 is going to be 6. Okay, so the instantaneous rate of change at this particular point 1, is going to be 6. All right, so what is a geometric interpretation of this number 6? Instantaneous, so the rate of change over some interval is the slope of the secant line. But on the other hand, the instantaneous rate of change at some particular point is the slope of the tangent line. So that is well visible from this figure. So once again, the rate of change is the slope of this line segment A and B. So now we take the limit as delta Q go to 0. Okay, that means this point Q2 is approaching Q0. So this, as Q2 approaches Q0, and this point B will get closer to point A. Okay, so the correspondingly, the secant line is going to be overlapped with this tangent line. So the instantaneous rate of change at some particular point indicates the slope of the tangent line to the graph at this point. So at the instantaneous rate of change at point A is the slope of the tangent line kg at this point. Right? So rate, once again, that is pretty important. Rate of change is the slope of the secant line. On the other hand, instantaneous rate of change indicates the slope of the tangent line. All right? And finally, the derivative. Okay? Once again, the derivative is the instantaneous rate of change. So the derivative is another name of that rate of change. Okay, so the derivative of f at x naught is defined as this expression. So instantaneous rate of change at point x naught, and usually denoted by f prime of x naught, or alternatively, it can be denoted by say df or dx. So here letter D stands for infinitesimal change in some variable. So df means infinitesimal change in function's value f, dx infinitesimal change in variable x. Okay, or because y is f of x, so we can express as dy over dx. Okay, so the rate of change is delta y over delta x, and the derivative is just the instantaneous rate of change. So by the same token, it is usually denoted by dy over dx. So that is just a rate of change when change in x is a infinitesimal. Okay, so we have here three equivalent expressions for derivative. F prime or df over dx or dy over dx. They all mean the same. They all mean the derivative. Okay, and so the derivative is defined as the limit, and we are going to talk about the existence of a limit in the next video. But if the limit exists, so the limit of this expression exists. So in other words, f prime x naught exists. So the derivative is well defined at that point x naught, then we say function is differentiable at that point. And if the function is differentiable at every point x, then we simply say function is differentiable. Okay? And once again, derivative is instantaneous rate of change. So the derivative stands for the slope of the tangent line at some specific point. Okay, so if we have a function f of x given by one quadratic function, then we can find f prime of 1, and we can find the equation of the tangent line to the graph at that point. So first, let me look for the derivative using this definition. So just to put in number 1 for x naught, then f of 1 plus h is a 3, 1 plus h squared, plus 5, 1 plus h minus 7, and f of 1 is 3 plus 5 minus 7, which is 1. So the numerator amounts to the difference between these two. So if I simplify this expression, then it's going to be 1 plus 6h plus 3h squared plus 5h. So 11h plus 3h squared plus 1. Okay, so the difference between these two, then 1 will be cancelled. So it's going to be just these two terms. Okay, and we take this and divide it by h, then it's going to be 11 plus 3h. Now we take the limit as h goes to 0. Then 3h goes away. As h is very close to 0, 3h also approaches 0, so it is going to be 11. So the instantaneous rate of change at 11, or in other words, the derivative at point 1, it turns out to be 11. That is the slope of the tangent line at that point. So using this information, we can figure out the equation, because whenever a linear equation has a slope a and passing through point b comma c, then its linear equation is a times x minus b plus c. Okay, so using this formula, we can construct the equation of the tangent line, which is a y equals slope 11, and at point 1, the corresponding y value is a 1. So we know this function passes through 1 comma 1, the point 1 comma 1. So x minus 1 plus 1, so 11x minus 10, which is going to be the equation of the tangent line. All right, so in this video, I introduced the comparative static analysis and also introduced the main mathematical tool for doing comparative static, that is the derivative. All right, hope you guys enjoyed this video. Then I will keep recording lecture videos. I'll see you guys in the next.